Okay, welcome back, everybody. Hope everyone's doing okay. Um, any questions about yesterday, the labs, uh, the course itself, where you can get information? Any question at all whatsoever? We did chapter one was pretty quick. Today we'll probably knock out chapter two and possibly chapter three. If not finish chapter three, definitely get into chapter three. So, we're moving along here. Um, Let me see. Uh, I did uploaded the recording. So if you can go up to the YouTube channel. Some students have subscribed to that channel, so whenever it's uploaded, it will alert you. So if you want to, listen to what we talked about that particular day. Now, they're fairly long, they're lengthy, obviously. So it does take time for one Zoom to convert it. It converts it to an MP3 format, and then when I upload it to YouTube, it converts it to its format. So it may take a few hours to get everything all the way up there, but I would try make every attempt to make sure that that day's Zoom recording is uploaded before the evening's out. Okay. All right. Since no questions, let us. Oh, I got one more person here. All right. We're good to go, I believe. Okay. So the next two chapters, we're going to kind of shift gears a little bit. Chapter one kind of introduces you to the chemical aspect about what we're going to talk about, and chemistry in general. And then, unfortunately, we're going to get into the math aspect of it. And that's basically the next two chapters. Um, we're going to be dealing mostly with converting units, meaning going from English to metric units, or staying within whatever units we're working with. In science, we will work with the metric units only, but in these particular chapters, we do some examples of going from one set of units to the other. Now, this whole exercise has a function, has a purpose, not only to teach you, to do the mathematics, but more importantly, to be able to go when we look. Eventually, we're going to get to the point where we're going to look at a chemical reaction and have, for example, A plus B reacting to give us C and D. We're going to be able to calculate, how much A do we need to react with B? Okay. And we have a specific technique, a process to allow you to help you get from that one point to the other. And it's all related to units, and it's all related to these ratios I mentioned last time we talked about a ratio, a factor. For example, driving, you're at a speed, you're dealing with miles per hour. So you have the ratio of the units miles per hour, which I can write as miles per hour, or I can invert that and write it as hours per mile. And which unit we set it up as depends on one, the units were given in the problem to begin with, and two, the units that we eventually are trying to keep track of and what we're looking for. Okay. And so we have a systematic approach to go after these problems and calculating, because sometimes you look at the problems and you're like, just don't make any rhyme or reason how to even attack the problem. But we're going to learn a technique to break it down into the steps. Okay. All right. So the other aspect that we're going to talk about is in this chapter has to do with significant digits. Basically, the thing to remember here in any measurement, okay, any measurement, no matter what type of measurements you're doing, there is at the last number, let's say you're measuring length, using, maybe a sophisticated laser beam. Okay. And when you measure it, you get, whatever length it is, 0.00, whatever numbers and whatever number of decimal points you get. But you know what? At the last decimal point, there's always a degree of uncertainty, meaning that any remeasurement has a degree of uncertainty. The other thing to remember is I'm sure you've done some mathematics where you typed in numbers, divided, multiply, whatever you did through your calculator, and you ended up with 20 digits. Your thinking may be, okay, let me present these 20 digits because it's pretty accurate. And my response to that is no, don't do that. Okay. You might be thinking you're adding accuracy to your answer, but you're not, because the number of digits, okay, let me state this. The number of digits that you present your answer in is dependent on the accuracy of your measurement tools. Okay. So earlier I mentioned, okay, I'm measuring the length using the laser beam. That's pretty accurate, right? Fairly accurate, and I can get a number of decimal places. However, if I'm measuring with a ruler, well, my accuracy diminishes compared to a laser beam. And if I use that number from a ruler measurement in whatever mathematics I need to do at the end, then I cannot be more accurate than the least accurate digit that I utilize. Okay? So let me restate that. I cannot be more accurate in presenting my answer than the least accurate digit that I use to do my mathematics, be it multiply, subtract, multiply, divide, add, or subtract. Okay. I'm getting signal that my internet connection is a little bit unstable. Let me shut off some applications. I can improve it a little bit better. All right. Okay. Now, the other thing I always hear is that mathematics, I really don't like mathematics. And that's okay. All right. But let me tell you right now, if you can add, subtract, multiply, divide, some very rudimentary algebra, that's all we're going to be doing. We're not going to be doing any sophisticated differential equations or anything like that at all. Multiply, divide, add, subtract. Okay. And then, of course, when I say algebra, I'm looking at units and realizing that if I divide A divided by A, my A's cancel and I end up with a 1. Okay. That I can, like units will cancel out if I divide them. Okay. But we'll have more examples on that here in a bit. Okay. So let's jump right in there. Okay, so chapter 2 deals with math skills. And there is obviously, do read the chapter, but there are practice problems in the module for this particular chapter. So I strongly suggest you take a look at them and try to do them. The key's there, but don't look at the key. Wait until you're done. Okay. And the more you practice in mathematics, the more easier it gets, basically. Okay. It becomes that is foreign. So get as much practice as you can. All right. So let's talk about measurements. Measurement is a number, obviously, but more importantly, it's a number with a unit. Okay. And without a unit, that number is meaningless. Okay. So, and that's important that we utilize the correct units, be it metric units or even the English units. But in science, we use metric units. We will be using English units in this particular chapter and the next chapter, simply to demonstrate how to convert from one unit to the other. Okay. So if, for example, if you weigh, what's wrong with this particular comment, it says the book weighs 8. Okay, that's fine and dandy, but what is 8 what? 8 tons, 8 pounds, 8 ounces, therefore, so units are important. All measurements have a degree of uncertainty, regardless of what instrument you have. Even the balances we looked at the lab, I don't know if you recall, we'll be using those balances. We can measure up to about 3 decimal places on that. But that last number is always a degree of uncertainty. Okay. And generally what happens, that last number, we estimate. And there's nothing wrong with doing that. You estimate the last number because that last number, you just depends on the instrument. You just give it a ballpark figure, so to speak. Okay. It doesn't mean your number is wrong. I might read something like 1.06. You might read it as 1.07. That's okay. Where because of that degree of uncertainty in the last measurement. So all measurements have a degree of uncertainty. Okay. Now in the metric units, we're going to measure obviously length. Length, we have units shown up here. We got cm per centimeter, mm for millimeter, m for meter, and km for kilometers. After we're done here, I'm going to show you a file which will encompass all these units and how to go from one unit to the other with respect to centimeters to millimeters or centimeters to meters or vice versa. Okay. All right. So measured length, obviously, we have maybe something like a ruler. Now, it depends on the ruler as far as how accurate you can do a measurement. So you can see hopefully that if which ruler here do you think you can get the most accurate with respect to a measurement? Do you think the white one or the brown one will give you more accurate measurement? Anybody want to give it a shot?
The brown one?
The brown one, exactly, because the brown one has more increments. In fact, the brown one you can estimate all the way to, something like, let's say we're going to measure, let's say we want to, let me put a mark here. Let's say everything's about a 0. Let's say we want to measure this red line. Okay. So in doing that, using the top ruler, the best I can do is you can see that mark is the halfway mark between the 3 and the 4. So it's at least a 3.5. And then maybe, my best mark is approximately 3.6. Okay, 3.6, and assuming here we're dealing with centimeters. Okay, so the white ruler, I can only go to 1/10 of a centimeter as far as my accuracy. Now, if I do the same thing with the bottom one, obviously I got 3.5, and I can estimate it is somewhere between the 0.5 and the 0.6, so maybe it is closer to 3.55, okay, centimeters. So here, I can go to the 100th place. The 100th place with respect to more accurate, because it's governed by the tool that I'm using to do this measurement. Okay. Now, if I take this measurement and I'm using this number to do some further mathematics, then that number on top using the white ruler will govern the accuracy of my final answer, which would be, depend what I'm doing to. And we're going to learn about how this works. If I'm using the bottom ruler, obviously I'm going to be more accurate. So my answer will be a little more accurate if I'm using the brown ruler, okay? So, and when we start talking about our digits, and I realized that, like I stated earlier, you can plug in these numbers in a calculator. Let's say you do mathematics and you're doing a multiplication, you end up with all these digits. You may be tempted to put all these digits in there, but we can't do that. We have to identify which is the least accurate measurement, so we can determine how many digits our true answer would have, our answer would have. Okay, so obviously the white one will have a lot more degree of uncertainty, okay? Because it's going to 1/10 of a centimeter compared to the 100th of a centimeter for the brown one. Okay, with respect to mass, units that we utilize are mg for milligrams, k for kilograms, g for grams, okay? We have different types of balances. The balance on the right is something that we utilize in the lab. You can see just by that picture that you can get to the third decimal point in that measurement. Where the one on the left is a triple beam balance, you might be able to get 1/10 of a gram, okay? 1/10 of a gram. So obviously the digital balance on the right is a lot more accurate than the one on the left, okay? Okay, mass versus weight, there is a difference, okay? Mass is mass is constant. So you have an X amount of mass, be it if you're here on the moon or here on Earth, I should say here on Earth or up in the moon, your mass is constant. Your weight, however, is governed by the force of gravity. And the relationship between the two is that weight is equal to mass times a gravitational constant, which is 9.8. We're not important here, but that's the difference between mass and weight. However, since we're kind of stuck here on Earth, we tend to interchange the two. That weight and mass seem to be the same. And keep it in mind that no, they're not the same. Weight is dependent on the effect of gravity has on your mass. So an astronaut that weighs 170 pounds here on Earth is going to weigh about 29 pounds on the moon, okay? Because the gravitational force on the moon is much, much less, about 1/6 less. All right, volume. Volume, the types of units that we utilize, the most common unit is the capital letter L, which stands for liters. It's like a 2-liter bottle, okay? But we also had the prefixes of kiloliters and milliliters. And here's some pieces of equipment here that we use to measure volume, things like beakers and flasks and graduated cylinders. So some of these are which we're going to use in the lab itself, okay? Now, syringes, a lot of syringes have the units of cc. Anybody know what cc stands for? Yeah, so you need 10 cc's of a particular shot. What kind of units are you being given? What do we got here? Milliliters, almost a milliliter, but cc stands for exactly.
Cubic centimeters?
You got it. Cubic centimeters represents a cc. So it's a volume measurement. So 1 centimeter times 1 centimeter times 1 centimeter and all three axes, that's cubic centimeters. Now, 1 cubic centimeter is equal to 1 milliliter. So here's your first conversion factor, okay? You got this one right here. So I can write this as a ratio where I got 1 milliliter on the numerator, 1 centimeter in the denominator. I can write it like that, or I can invert it, where I got 1 centimeter in the numerator and 1 milliliter in the denominator, okay? So every ratio I can set up in this manner, every ratio. And now which one I use depends on the question asked. So for example, if the question says, you have 10 centimeters, how many millimeters does that equate to? Is the question, okay? So what you're trying to do is to get to the units of milliliters and get rid of the units of centimeters. Well, the units that you are looking for in that problem will always be in the numerator. And the units that you want to get rid of will always be in the denominator. So I would use this factor on the left and multiply 10 centimeters times the factor on the left. Notice that my centimeters cancel out, leaving me with units of milliliters. So 10 centimeters is equal to 10 milliliters, okay? This is pretty straightforward one-to-one relationship, but sometimes there's relationships that are not a one-to-one, okay? Notice what I did here. This is a technique I'm going to utilize and continue to utilize when we get to calculations, chemical calculations, but keeping track of the units. I know given the conversion factor up here, 1 milliliter is equal to 1 cubic centimeter, that I've amassed a problem that if I have 10, convert 10 centimeters into milliliters, okay? So knowing what units I'm looking for tells me that milliliters has to be in the numerator and centimeters has to be in the denominator. That means I'm using the factor on the left. And then as I multiply 10 centimeters by the unit, my units cancel out, leaving me with units of milliliters, which is what are the units that I'm gathering. We will eventually, okay, set problems up where we're going to have at least minimum three conversion factors. In fact, when we get into a little more detail, I'm going to show you, demonstrate to you a conversion factor with some outrageous units that just don't make sense. You know, the question is, I used it when I was teaching dental hygiene students. I needed to convert, I forget what it was, how many bananas, I believe, is equal to dental hygiene students. Crazy, right? That's okay. But the point of the exercise was if you have conversion factors, we can go from point A to point B. Okay, and I'll go through that example here later on. Okay, now for English units, specifically volume, there's something here that helps you. For example, this picture. Notice there's a big G on the outside, okay? There's one big G here. Notice that there are 4 Q's within the big G. So what that says is there are, in 1 gallon, there are 4 quarts, okay? Now, if you look within the Q, there are 2 P's. And what that tells you is that in 1 quart, there are 2 pints, okay? And then if you look at the individual P, there are 2 C's within that. That tells you that there's 1 pint is equal to 2 cups. So notice the conversion factors you have on top. These ratios that you can set up with either gallons in the numerator or gallons in the denominator. Okay, quarts in the numerator, quarts in the denominator, and the same with the other pints and cups. Okay, to help you to go from one set of units to the other. Okay, so it's a little tool here to help you within the units. Okay, let's talk about reading volume within the cylinder. And we're going to be doing this in the lab. Okay, you can actually be measuring the volume. Now, what happens due to the properties of the liquid is that when the liquid is in the cylinder, it's not a flat image on top. It actually forms this concave shape. which is called the meniscus, okay? So the liquid forms this concave shape we call meniscus, okay? And the way we read the volume is that if I'm looking at it from this direction right here, I'm reading the bottom of the meniscus, okay? It's a bad drawing here, but to read that volume, I first of all check the container that I'm in and make sure that I'm at the 0 point right here. So my cylinder starts 0 at the bottom and goes up positive numbers in the up direction. So that makes sure that you're reading the number correctly at where the liquid's at, okay? So check, because you can have a container where it's reversed, where the 0 starts on top. So you work your way down when you read it. So when you read this, now you read the bottom of the meniscus, and what do you guys think this measurement will be? If you had to put a value on this measurement, what do you think? What would be this measurement right here?
22.5.
Okay, 22. All right, well, let's take a look at that. 0.5 looks reasonable. Yeah, how about the 22? You look at your increments here. All the increments are 5. This would be 6, 7, 8, 9. So each line represents an increment of 1, right? And so the first increment after 20, what would that be?
21.
Exactly, it'd be 21. And now the 0.5 is reasonable, or if you read a little bit more, 0.6, that's reasonable too, or even if you read it 0.4. So 21.5 is a good measurement, okay? And notice that because of the number of increments, the best I can do, because of the instrument I'm using to measure, the best I can do is 1/10 of a milliliter. I cannot go further than that because I don't have the equipment. The equipment does not allow any more precision, okay? You might be tempted to throw another number in there, but don't do that because your instrument is not that accurate. So 21.5 would be a reasonable number, you know, and even from my perspective, it could even be 0.6, but a 0.5 would be good. Okay. So don't be tempted to just look at that and say, okay, 21.50, okay? Even if you were to present this number, 21.50, that would be inaccurate. Again, because you don't have equipment that can measure to the 100 place, okay? Let me reemphasize that, okay? You might be tempted to add a 0 there and present that as your number. And what you have done, you have added accuracy to that measurement on your own. It's not governed by the tool that you're using. The tool that you're using, this graduated cylinder, can only read to the 1/10 of a milliliter, to the 10th position. And by adding a 0, you have increased the decimal places. You increase manually, erroneously, the accuracy of that graduated cylinder, okay? So this would be an incorrect statement because you don't have that accurate of a piece of equipment to present that data. All right, so we're going to be talking about what we call significant figures, or digits, okay? And basically what they're saying is, okay, do these digits play a role in making sure that when I present my final answer, that I have the correct number of significant digits? And that's what's all it's going to eventually be, we're going to be talking about, okay? And we have to identify which digits are considered significant and which are not. Okay. Now, it doesn't mean that that digit, even though it's classified as insignificant, that it doesn't count. It doesn't mean that at all. When we talk about significance with respect to digits, we're talking about, do these digits play a role in the final answer that you present? And with that, you would keep it in mind that you cannot be more accurate than the least accurate number that you have, or the least accurate measurement that you have. Okay. And so obviously, if you look at a bathroom scale versus a surgical scale, yeah, the surgical scale is going to have a lot more significant figures. Okay, a lot more accurate. Okay. We went through this exercise earlier with a different ruler, but you can see here, we're going to take this measurement that the top ruler at the best I can do is 1/10 of a centimeter. Let's assume this is centimeters. Whereas down at the bottom, I can do a little bit more. So for example, maybe I can see it's, I go, here's 29, here's 30. That tells me that 20.5 is about right there. So maybe 29.2. Would you agree? Okay. Whereas if you look at this one, I got more increments here, so my accuracy goes up to the 100 place. So maybe definitely 29.2. And then that's the last one that you were guesstimating. So I'm just going to guesstimate here at 29.25 for that measurement. Okay. See how that works? And so the least accurate number is this one, and the more accurate number is this one. Okay. And again, that is governed by the accuracy of the instrument that you utilize to do that measurement, be it length, volume, or mass. Okay, which brings us to the concept of significant figures. And this can be challenging at times, but keep this in mind. When we talk about significant figures, keep in mind that what we eventually going to present is an answer. We're going to do something mathematically with these numbers, okay? Because we did a measurement, and then these measurements are going to be utilized in some type of mathematical function. And when we do that, we all know that the calculator can present, 30 digits. But it would be inaccurate to present 30 digits because the answer is governed by the least accurate measurement that you utilize. Okay, here's the whole thing is right there. Your answer cannot be more accurate than the least accurate digit you utilize in whatever mathematical function you did. And like I stated, what we're doing mathematically is adding, subtracting, multiplying, dividing. That's it. Okay. So we have to identify what is considered significant. And so we classify it as significant. It only is significant with respect to the final answer as far as digits, number of digits to present. Does not mean its value is not significant. Okay, it doesn't have nothing to do with the magnitude of the number or the value of the number. All right, so for example, all numbers from 1 through 9 are considered significant. So if we look at a number as 4895.2, that number has 5 sig figs. 5 sig figs. They're all integers and they all count. Pretty straightforward. Integers always count. No questions there, right? Where the confusion seems to fall is when we talk about the zeros. Sometimes zeros do not, well, sometimes, a lot of times zeros don't count as being significant, but there are examples where zeros do count with respect to being significant. Okay, so for example, leading zeros in this decimal number here, 0.000, all of those zeros up front, okay, are not considered significant. All they're doing is holding the decimal place. That's it. So those zeros would not be a factor, would not play a role in the final number of significant figures that your answer would be in if I were to use that number in some mathematical function. Okay, so this example, we have 0.0005454. Well, all integers count, so there's only 4 sig figs in that digit. Okay, now with that being said, there, if I were to do some function, mathematical function with the number, this number, and this number, my answer should not have more than 4 sig figs at the end. Okay, because why? Because this number is the least accurate number between the two that I'm working with. All right. Okay. We'll give you some more specific examples here in a bit. Now, zeros that are in between integers, they count as being significant. Okay. For example, we have 3050. Well, in this case, this zero here between the 3 and 5 is captive zero, so they're considered significant, whereas the other zero is not. Okay, I'm going to have two questions for you to ask yourself when you look at zeros, okay, to help you determine whether they're significant or not. We'll get to that here in a second. So 3050 contains only 3 sig figs. That last zero does not count. All right, the number 0.00 and then 2001 has 4 sig figs. These are leading zeros as per rule number 2, so they don't count. These zeros as per rule number 3 are captive, so they do count. So that number has 4 sig figs. Okay, 4 sig figs. All right. And then trailing zeros meaning zeros after a decimal point and a integer always count. And there's the question to ask yourself with respect to zeros, because those are the ones that can be ambiguous and could be like, I'm not sure. But if you ask yourself 2 questions, first of all, let's look at the leading zero, 0.0880. Okay. The 2 questions to ask is there an integer up front of those zeros? And the second question is there a decimal point anywhere in that number? Okay. If you answer yes to both of those questions with respect to the zeros you're looking at, then those zeros count. If you answer no to any of those 2 questions, then those zeros don't count. So let's take a look at these zeros, which we know they're leading zeros, but let's assume you forgot that rule about leading zeros. So you ask the question for these zeros here, is there an integer in front of those zeros? The answer is no. There's no zero in front of these 2. That means that those 2 zeros up front do not count. Okay. All right, let's look at the last zero here. You're sitting there looking, well, maybe it counts, maybe it doesn't, I'm not sure, but you know the questions to ask. Question number 1, is there an integer in front of this zero? And the answer is yes, there's an 8. Okay, so we got a yes for the first question. Okay, second question, is there a decimal point anywhere in that number? And sure enough, it's up right there. So we got a yes for that question. So what that tells you is that implies that zero is considered significant. So we have 3 sig figs in this number. Okay, 3 sig figs. Look at this number right here. 28,500. Obviously, the 2, the 8, and the 5, because they're all non-zero integers count. They count. But you're not sure about the 2 zeros, okay? So you ask the question again, is there an integer in front of those 2 zeros? And this is yes. Okay, yes, there is. All right, so that one's okay. Second question, is there a decimal point anywhere in that number? And the answer is no. That means those 2 zeros after the 5 do not count. We have a total of 3 sig figs. Okay. Now, if we were going to do something mathematically between, let's say, this number and this number, okay, our answer should be no more accurate than the least accurate number. We're going to multiply those 2 numbers or divide them. Okay. It'd be no more accurate than the 3 sig fig number. Right. So adding decimal points makes all zeros count except the leading zeros, okay? Because there's no integer in front. But after that, if there's an integer and there's a decimal point, it will make those zeros count. So when we look at 2 numbers here, okay, 285 versus 285.00, well, there are 5 sig figs here versus 3 sig figs for 285. Okay, because again, those 2 zeros, there's an integer up front on both of those numbers, and there's a decimal point in front, so those zeros count. Any questions up to this point? All right, now this is where we learn about determining if these numbers are significant or not, okay? And what's happening is that these numbers, if we think about it, these numbers have a degree of uncertainty. A lot of them are going to be measurements. And whenever you have any measurement, length, volume, and mass, there's always a degree of uncertainty, okay? Always a degree of uncertainty in any type of measurement. But there are cases where we have exact numbers. They're not measurements. For example, if you want to describe how many people you have, you got 14 people. That number 14 is an exact number, and therefore would not play a role in determining how many sig figs your final answer would have. A conversion factor like 3 feet per yard, that's an exact number. There's exactly 3 feet in 1 yard. Not 3.6, 3.2, exactly 3 feet, and therefore would not play a role. It's an exact number. 100 pennies per dollar, count 5 iPads or a 12-pack. Those are exact numbers. So recognize the numbers you utilize in your mathematics, and if anything is exact, then they will not play a role in determining how many sig figs your final answer would have. The other numbers that you do not play a role in sig figs are the atomic weights of all the elements. If you look at the atomic weight right below the symbol, there is a number which is a decimal number. For example, carbon has an atomic weight of 12.01 grams per mole. Okay, that number is a decimal. You might think that is a measurement, but it's not. And so we're going to learn why that's not the case. But just keep in mind that the atomic weights of the elements are not exact and would not play a role in determining sig figs in your final answer. Things that are measured, any measurement, as I stated, 7 inches, 200 pounds, 10 ounces. We're measuring length and mass and volume here. There's always a degree of uncertainty. So those numbers are not exact and therefore could play a role in determining how many sig figs your final answer would have. Okay? So anything measured is not an exact quantity. Okay. So we'll see that sig fig rules don't apply to exact numbers, so they will not be a factor in sig fig. So let's take a look at these numbers here. 5.05 centimeters. How many sig figs do you think that number represents? I want to take a shot at that. 5.05. Three sig figs, exactly. That's good. Three sig figs. You might think the zero. Well, what about the zero? Well, the zero fulfills two rules. One, it's a captive zero. It's between two integers, so automatically you don't need to go any further. But let's say you forgot. You forgot that rule. You ask those two questions. Is there an integer in front of that zero? Yes, there is. There's a 5. And then is there a decimal point anywhere in that number? Yes, there is, right after the 5. So yes, that zero counts. Okay. So there would be 3 sig figs. What about 1200? How many sig figs? What do you guys think?
2,
2, exactly. The 1 and the 2 are the only ones that count. Those 2 zeros, yes, there is an integer in front of those 2 zeros, but there's no decimal point anywhere in that number. Therefore, those 2 zeros would not count and as being significant. They do count as holding the magnitude. Now, don't do this mistake, because thinking that the zeros don't count, that when you eventually going to get to round things up, that these two numbers are the same, 1200 versus 12 versus 1200. Obviously, are these two numbers the same, 1200 versus 12 versus 1200?
no.
No, of course not. Of course not. And so we wouldn't drop these zeros. They're still important because they hold the magnitude. If you don't see it, put a dollar bill in front of dollar symbol. Okay, I got $12 versus $1,200. Okay, quite a difference, right? So we don't want to drop these zeros totally away, thinking because we classify them as insignificant that they don't count. Yeah, they do count. They do count with respect to the value, the magnitude of that number you're working with. Okay, good. All right, what about the next one? How many sig figs do you think we have in that particular number?
4.
We got 4, exactly. The first 2 zeros, the rule of leading zeros, they don't count. But again, I refer you back, and I sound redundant. That's okay. I'm going to be redundant because I can't overemphasize this. Look at those 2 zeros up front, ask those 2 questions. Is there an integer in front of those 2 zeros up front? And the answer is no. Being no means they don't count as being significant. The other 2 zeros, you can go and ask the same question. Is there an integer in front of those 2 zeros? And the answer is yes. Is there a decimal point anywhere in that number? Answer is yes. So they count. So we got 4 sig figs there. Okay. The next one, we only have 1. Those 4 zeros up front, in front of the 5, are leading zeros. And so therefore will not play a role with respect to being significant figures. 50 would have one sig fig. Okay.
I have a quick question.
Sure, go ahead.
So the 1200 milliliters and
Yeah.
the 50 feet, why does those two, oh, I guess it doesn't count. Never mind. So it doesn't count for sig figs. It just counts with respect to the measurement.
Yeah, exactly. They count when we're dealing here, and that's important. We got to keep the 2 separate things separate. When we're talking sig figs, we're trying to play a role. We're actually trying to figure out which number is the least accurate. So to date, of the ones we've done, the least accurate measurements here are the last 2 numbers. You see that? They only have 1 sig figs. The most accurate measurement is the one with 4 sig figs, the 3rd entry. And then the others are in between. So we have to identify how many sig figs we are working with, because we could be, let's say, take these 2 numbers right here, and maybe we're going to either multiply or divide these 2 numbers. okay, to get some answer. And if you do that, you will see your calculator split out a bunch of numbers. But the thing to remember is this, and we're going to learn about the rounding of your number and your answer, that our final answer should not be more accurate than that digit that contains the least number of sig figs. So in this case, the least accurate number is the 1200. The zeros place the magnitude. Okay, we're at the 1200 range. We don't eliminate the fact that those zeros are holding our decimal place and we were in the 1200. It's like the example I was saying earlier, you know, $12 versus $1,200. Which one do you want? Would you rather have? Well, obviously the bottom one, right? So even though these two zeros here don't play a role as far as sig figs, they do play a role with respect to magnitude, okay, with magnitude. And the sig fig business is just trying for us to figure out how many sig figs we have in our digits, so that when we do something mathematically, we cannot be more accurate in our answer than the least accurate digit. Okay. So for example, the next one here, 50.00. Okay, that has 4 sig figs. Can you see that? Okay, I mean,
I have a question about the exact number.
yes.
So for like the exact numbers, like if it was, are all exact numbers 1 sig fig, or if it was like 3 digits but with no zeros in it, would it be 3 significant figures?
What exact numbers, we don't use the sig figs. When we talk about exact numbers, like when I say a dozen, how many, what's the number for a dozen? Dozen has how many numbers? What's the quantity for 1 dozen? 12, right?
Yeah.
So the 12 is an exact number because there's exactly 12 items in the dozen. Okay, so the sig figs would not play a role in that at all. So if I said a dozen, even if I said half a dozen, the examples I did earlier was 3 feet per yard. That's the conversion factor. 3 feet is exactly 3 feet in 1 yard. Or there's 100 pennies in the dollar, right? Exactly 100 pennies in $1. Those are exact numbers. And so we don't look at the sig figs for exact numbers.
Okay, thank you.
Yeah, does that clarify a little bit?
Yes, thank you.
Most of the time, I can't think. I think the majority of the time, exact numbers are not really like measurements, something like you measure length, volume, mass. They are a particular number. Okay, so if we look at the next two, like 50 and 50.00, 50 only has 1 sig fig. 50.00 has 4 sig figs. So maybe what's happened here, we got a measurement. Now, these two numbers, you know, are 50. If I were to put $50 up front, it's $50 for both of them. They differ in the accuracy of that measurement. Okay, so this one here maybe got measured with a ruler, whereas this one here maybe got measured with a laser beam. Shot a laser beam, and I was able to get an accurate reading of 50.00. So obviously I have more decimal places, I have more digits, I have more accuracy with the 50.00, and therefore I have more sig figs, okay? As compared to this one, 50, which it could have been a small ruler. I could have even eyeballed it. Oh yeah, it looks like 50 feet, okay? My eyes are human eyes versus a laser beam is not that accurate in measurement. Okay, you see the difference here between these two? Hopefully. All right, next one. 123.45. Well, they're all integers. No question about it. There's 5 sig figs, and then the last one has 3 sig figs. The last zero, ask the question, is there an integer in front of it? Yeah, there is. The last zero, there's a 9 in front of that zero. Okay. Is there a decimal point anywhere in that number? The answer is no. Therefore, that zero would not be considered as being significant. Okay. So that number only has 3 sig figs. And so now, once we identify how many sig figs we have, now when we do the mathematics, and we're going to break the mathematics into 2 different areas, okay? One, we're either gonna multiply or divide, or we're gonna add and subtract, okay? And the difference between the two is when we multiply and divide, we look at sig figs to determine our final answer, how many sig figs our final answer would have. So if I were going to multiply or divide, let's say this number versus this number, our answer should have no more than 2 sig figs. Okay. Now, when it comes to adding and subtracting, what we look at is decimal places. We haven't gone away from accuracy, because if I look at a number like 10.1 versus 10.12, you can see which of these 2 numbers is the least accurate number, 10.1 or 10.12. What do you guys think?
$10.1.
Exactly, 10.1. That is the least accurate number with 1 decimal point. That means our final answer should not have more than 1 decimal point. Okay, because what's governing our answer with respect to accuracy is the least accurate number, be it we add or subtract, be it we multiply or divide. It's just how we go about and figuring it out is a little bit different. When we multiply and divide, we look at the sig figs. When we add and subtract, we look at the decimal places. Don't mix and match the two. Okay. Don't think sig figs with respect to decimal places. But we'll have specific examples here in a bit, so hopefully come a little bit clearer. This is just a flow chart. You know, does 0 follow an integer or decimal number? Kind of help you out with respect to zeros. The zeros tend to be the ambiguous part where, you know, students get confused. But if you ask those 2 questions, is there an integer in front of the 0? Is there a decimal point anywhere in that number? Then that 0 counts as being significant. Otherwise, a no to any of those 2 answers means that that particular 0 does not play a role in determining sig figs. All right, now this will help start us to put everything together. We identified how many sig figs. I told you about multiplying and dividing. That's going to be governed by the least number of sig figs. I talked to you about adding and subtracting. That's the final answer is going to be governed by the least number of decimal places. But the question is, we got to truncate that number. We do the mathematics, we end up like a number this big, okay? We have to figure out where to cut it off, and we got to round that number, okay? So this part's about rounding. And the number and the rule is fairly straightforward. Let's take 5.4, okay? It's asking you to round to 1 sig fig. Well, 1 sig fig is this position right there, the first number, okay? What we do is then look at the neighbor and then follow the rules up here. If that neighbor is less than 5, okay, the number that we need to truncate stays the same, okay? So in this case, the 5 here remains 5, and that's our answer. We drop the 0.4, okay? If for example, one sig fig again, we mark that position. We look at the neighbor. If that number is greater than 5 or equal to 5, then that number that we're going to truncate goes up. So this 5 becomes 6. Okay, straightforward rule. We're only looking at the immediate neighbor. We don't care what is happening down the road. And I've seen this happen quite a bit. Don't do this, okay? We're only going to one sig fig position. So we're just looking at the immediate neighbor. And you might be tempted to do a rounding thing from way over here. No, don't do that. We just care about the number immediately to the right of the number that you're going to truncate at. Don't care what's happening down the field, okay? And there's no rounding going on. Don't round to 6. This brings to 8, and then it goes to 9, then it goes to 10. No, don't do that at all. Just immediate neighbor, okay? Don't change the magnitude of the number. For example, along the lines I was talking about. Let's say you have the number 5,400 down here, and they're asking you to round it to one digit, one sig fig, okay? So that is the first number right there, the 5. So we look at the neighbor is a 4, so that 5 remains a 5. Okay, so we drop everything, the 4, the zeros remain 0, so our magnitude is 5,000. Here's the thing to remember to help you. When you have a number to look at, I put a dollar symbol in there in front. We can relate to money big time, right? So with 5,400 with a dollar symbol in there, I'm at the $5,000 mark, right? And so my answer should be in the $5,000 magnitude. I don't drop these zeros because guess what? If I do that, I have changed the magnitude to $5. That's a big factor of 1,000 that I've done. I lost the magnitude. Okay, so one kind of a rule to remember is this. All right, so using this example we just did down here, we're going to round it to one sig fig. So we're going to round it to the 5 here. We look at the neighbor. Okay, so numbers after the decimal point. After the decimal point, we can drop. You're not going to change the magnitude, okay, by adding zeros back in here. You will change the number of significant figures if you put zeros after the decimal point. So what we do is you drop that. Any number that is not a 0 before the decimal point gets converted to 0. So that 4 becomes 0. Okay, so you're at 5,000, not at 5. Okay, so be aware of the magnitude you're at, and the best little kind of rule to look at is right before you do anything, look at the magnitude of the number, like 5,400. That you're in the 5,000 mark. Okay, so your answer should be in the 5,000 mark. If it's not, you have changed the magnitude of the number, which is not what you want to do. All right, let me tell you what, I got 2:35. Let's take a 10-minute break. And I got, let's call it 2:45. Take a 10-minute break, and then we'll continue with this particular chapter. Okay, be right back. Okay, let us continue. All right, now, in this particular exercise, what they're asking you to round off these numbers to the three significant digits, okay? So you begin by first determining where the three sig fig position is. So starting from the far left, working your way in, mark the three sig fig position. So we go 1, 2, 3. The 3 is the three sig fig position in this particular number, okay? And we look at the neighbor, the immediate neighbor, which is a 7, and the immediate neighbor 7, which is greater than 5, means that that 3 gets pushed up to a 4. So the answer is 1.84 centimeters. Okay? And the other numbers, a 7 and a 4, get dropped. Okay. Now, you might be tempted, let's say if you were to do 8.4 and then you took the 7 and the 4 and converted to 0. What has occurred here by taking the 7 and the 4 and making them into 0? What's the difference between these two numbers? What do you guys think? Okay, what I did here in the second example, I said, okay, the 7 and the 4, instead of dropping them, what if I put zeros to replace them? What in effect has occurred by doing that? Okay, because we know that 184 has 3 sig figs, right? How many sig figs does this one have now? 1.8400. How many sig figs does that number have?
5.
Exactly 5. So by not dropping the 7 and the 4 and substituting zeros, you have added accuracy, but they're asking you to truncate, to cut it off at the 3 sig fig position. Okay, these two numbers, 1.84, 1.8400, are both the same number. The difference is that the 1.8400 is a lot more accurate with respect to, if it was a measurement, in this case, yes, centimeters. I can go to the 4th decimal point. Okay, all right, good. So there's our 3 sig fig position. Okay, look at our neighbor. Our answer is 1.84. And this is what we're talking about when we do the mathematics. And we're multiplying or dividing. And so our answer is governed by a number that had 3 sig figs. So we do the mathematics and we end up with this big number, 1.8374. Well, we can't present that as your answer because you're not that accurate. You're not that accurate with respect to going to 4 decimal places. So you have to determine that, I may have multiplied 2 numbers with 3 sig figs. So our answer should only have 3 sig figs. So I have to go through the rounding step so I can truncate it, cut it off at the 3 sig fig position. Okay. All right, here we have this one, $7,162.32. They're asking you to round that number off to 3 sig figs. First point to look at this number and look and see what magnitude you're at. You are at the $7,000 mark. Okay, so your answer should be somewhere in the $7,000 mark. Okay, notice I have a decimal point. 3 sig figs means that I'm going to truncate it right there at the 6. So that 2 before the decimal point, I need to convert that to a 0. And the other numbers after the decimal point, I can drop. Okay, so I look at the neighbor, and the neighbor is 2. So that 6 remains a 6. Okay, thing about rounding, I forgot to mention, is that number that you're going to round, it's either going to stay whatever number it is, or it's going to be bumped up to the next one. Depends on the neighbor. But it won't ever go down of whatever value is. It's either going to remain the same or go up 1. Okay, so here this number is 7,160, not 716. Okay, and that's what happens when that 2 before the decimal point gets dropped. You have changed the magnitude, $7,000 versus $700. Big difference. Okay. All right. So here we have a number which is less than 1. Remember that those are leading zeros, so they do not play a role in sig figs. So we go to the first integer in this case, and then go to the right to the 3 sig fig position, which is the 1 after the 3. Okay. We look at the neighbor, and neighbor is a 1, so that one remains a 1. So our answer is 0.00131 millimeters. Okay. All right. Again, that answer here for number 3, that could have been the result of whatever you did mathematically. Your calculator spits out that number, but you can't present that number because you're not that accurate. Okay, so your accuracy is governed by some digit you use that had 3 sig figs. So your answer should have no more than 3 sig figs in its answer to present as an answer. Okay, and then you got the 24,925. The 3 sig fig position is right on that 9. We look at the neighbor. Neighbor is a 2, so that means that 9 remains a 9. That 2 and that 5, because it is in front of the decimal point, gets converted to 0. So we have 24,900 inches. Okay, not 249. 249 means you have dropped the magnitude because you're in the 24,000 range. So key points about rounding: drop numbers after the decimal point. Okay, if they're after a decimal point, just drop them. It's not changing the magnitude of your number. If it's numbers before the decimal point, then those you definitely have to convert those to zeros. Otherwise, you do change the magnitude of the number that you began with. All right. Well, since we started learning about sig figs now, I have mentioned to you that we're going to do mathematics to these numbers. And again, we cannot present our data, our answer, as more accurate than the least accurate number we have to begin with. So the rule is this: we're going to add and subtract, which is two mathematical functions, and then multiply and divide. 2 separate things. So when you are doing whatever calculation you're doing, make sure you understand what are you doing mathematically. If I'm adding and subtracting these numbers, then the thing to remember is think decimal places. Okay, adding and subtracting, think decimal places, and that you can't be more accurate than that number that contains the least number of decimal places. Okay. For example, let's take 13.5478 feet, and we're going to subtract 11.20 feet. Okay, so notice there's 2 different numbers here, obviously, but different accuracy. The first one, I can go to the 4, it goes to the 4th decimal point. So there was a very accurate piece of equipment to measure that. But the next one, the 11.20, whatever they utilize to measure that is not as accurate as the first one. That only goes to the 100 place, 2 decimal places. Okay, so right away, you should see that I'm subtracting, and this could be true if I was adding, that my answer should not contain more than 2 decimal places, because that is the 11.20 is the least accurate digit of those 2 numbers I'm doing the mathematics to. So you do the math. Don't truncate anything beforehand. Just carry out the whole thing. Okay, carry it out. And you can see here now, we're going to have to truncate at the second decimal point. So we do the rounding like we've been doing. We're going to truncate at the 4. That's the second decimal point right here, decimal place. So the 7 is greater than 5, so that 4 becomes 5. So our answer is 2.35 feet. Okay. And that's only carry out to 2 decimal places, because the least accurate number with respect to measurement is the 11.20, only 2 decimal places. Okay. Your answer, if you were to present it as 2.3478, and that is an answer, would be incorrect, because the 11.20 is what's going to govern your final answer. That is the least accurate number. Okay. Now, sig figs do not play a role here. Okay, and sometimes the questions that are asked, they throw in the word sig figs when you're multiplying and subtracting. Don't let that confuse you. For example, let me ask you a question. How many sig figs does 2.35 feet have?
3.
You got it. 3 sig figs. Okay. All right. How many sig figs does 11.20 have?
3.
No. Try
4.
again. 4, exactly. Remember that 0? Ask the question. There's an integer in front of it. There's a decimal point, so that 0 counts. Okay. And then finally, how many sig figs for the last number, 13.5478?
6.
You got it, 6 of them. Okay. So notice that the numbers that we utilize, both in the mathematics that we did, and this is also true if I'm going to add, that I got 6 sig figs, 4 sig figs, and then my answer ends up with 3 sig figs. So sig figs are not a factor in determining your final answer when you add and subtract. I can't overemphasize that. When you add and subtract, okay, think decimal places and have that number that has the least number of decimal places will govern how many decimal places your answer would have. Okay, so sig figs don't play a role here. Okay, sig figs do play a role when you multiply and divide. Okay, so add, subtract, think decimal places. Multiply and divide, think sig figs. All right. Focus on decimal places with respect to adding and subtracting. So the question is this: when you look at the problem that you need to calculate, the first thing to ask yourself, what am I doing mathematically? Regardless of what the question sometimes says, present your data with the correct sig figs. Okay, that's fine. Some of these questions are, just written in that manner. I'm trying to correct them as I find them. But when you look at that problem, the first question to ask yourself is, what am I doing mathematically? Am I adding and subtracting or multiplying and dividing? If I'm adding and subtracting, think decimal places, okay? I'm multiplying and dividing in the mathematics, then I got to think sig figs. We're going to run through some examples on that. All this here is just to refresh your memory with respect to the decimal places, the 10 place, 100 place, 1,000 place, so forth and so forth. This is refresher. Now, let's get to multiplication and division, okay? So what we do here is we look at the numbers that we're either going to multiply or divide, determine how many sig figs each number has. From that information, that number that contains the least number of sig figs will govern how many sig figs our answer has. Okay, so multiplication and division, focus on sig figs. Okay? Your answer should have the same number of sig figs as that number which has the least number of sig figs. It may sound like it's two different things going on here, but it's the same thing with respect to accuracy. When we talk about adding and subtracting, the least number of decimal places tells us that's the least accurate number. When we multiply and divide, that least number of sig figs tells us that is the least accurate number that we're going to have, that's going to govern how many sig figs our answer would have. It's all about accuracy. All right, so we have this number here of 3.546 times 1.4. So the first number, how many sig figs does this number have? 3.546.
4.
We got 4 sig figs. That's good. What about the 1.4?
2.
We got 2. Good. Now, our answer would have how many sig figs now? What is the most
2.
number? 2, exactly, because it's governed by the number that has the least number of sig figs. All right, so since 1.4 has 2 sig figs, that is governing how many sig figs our answer would have. Even if we were dividing these numbers, same scenario, okay? So do the math, carry the number out completely. Don't truncate anything beforehand. And notice here, don't forget our units. Here's a little bit of elemental algebra that we're going to work with. Don't forget, we got meters times meters gives me meter square. Okay. Meters times meter gives me meter square. And if I were to multiply that by meters again, it would be meters cubed. Okay. Notice the number we get is 4.9644. So we go to the, let me change the color here a little bit. Since this had 2 sig figs, we go to the 2 sig fig position, which is the 9. Okay, starting from left to right. The 9 is our 2 sig fig position. We look at the neighbor. The neighbor is greater than 5. So therefore that 9 gets kicked up to 10. We carry the 1. So our answer is 5.0 meters square. Okay, 5.0 meters square. Right, and this has 2 sig figs, just like the one that had 2 sig figs to begin with. So the 1.4 determine how many sig figs our answer would have. So focus on sig figs when it comes to multiplication and division of your numbers. And don't forget your units when you're multiplying units. You know, just a quick refresher. Anybody know, remember, if you got m squared divided by m, what would be our answer? What we got here? M, you are correct, 100%. So another way to write m squared is to say m times m divided by m. And so notice that one set of m's disappears. So we got left over m, okay? So you may want to go back and refresh your nothing complicated with respect to algebra, just real, straightforward, simple algebra where units cancel, or, the difference is this. So m plus m will be equal to what?
M squared.
Ooh, not quite. If it was m times m, yes, that would be m squared, like you did right here. But m plus m would be equal to 2m, exactly. 2m. Okay, like banana plus banana, I got 2 bananas. Okay, plus banana, 3 bananas. Okay, so, but when I'm multiplying, and if I go m divided by m, you obviously m cancel out, that's equal to 1. Okay, And I state this because we're going to be talking about units and conversion and units canceling out. So, I use letters M, but that could have been easily, inch plus inch would have given me 2 inch. Okay. Inch times inch would have given me inch squared. Inch divided by inch would equal to 1. All right. All right, so let me overemphasize this. Don't mean to be redundant, but I have to. Adding, subtracting, focus on decimal places. Your answer should not have more decimal places than that number with the least number of decimal places. Multiplication and division. Focus on sig figs. Determine how many sig figs you have in your numbers that you're going to do the mathematics, and then determine who's going to govern how many sig figs your answer has. And the number with the least number of sig figs, which is the least accurate, will govern how many sig figs your answer has. Okay? All right. Which brings us to what we call scientific notation. Now, hopefully you have a calculator, scientific calculator. I know the calculator on the computers have scientific notation, at least the Windows. I'm not sure about Apple or anything, but you will need a calculator that can do what's called scientific notation. And what that is just a shorthand way of writing extremely large numbers or extremely small numbers, like listed here. There's a very large number on it right there, 1, 5, 6, 7, 3, so on and so forth. Now, most calculators, after about X number of digits, won't take any more digits in your system. There's a limit, be it large numbers or be it small number, like the bottom number, where it's decimal number 0.0000, etc. And to circumvent that, scientific calculators allow you to put in these large or very small numbers in the format called scientific notation. Scientific notation is just a format, okay, to write these small or large numbers. Okay, so for example, let's take this large number here, 93 million, approximately the distance from the Earth to the Sun, 93 million miles. Now, the way we do this, first of all, we're going to have I'm going to write the letter A times 10 to the X format, okay? And so we have a number A, whatever that may be, we'll explain here in a second, times 10 to something in the X power, okay? That's the general format that we'll be utilizing. Now, the thing about the number A, there's always going to be a number up front, a integer up front. You will never have a 0, it'll be an integer up front, okay? So an X represents how many decimal places we move the decimal place from right to left. Cool, let's take a look at this here, 93 million. This is where the decimal point would be, correct? So what we do is we count the number of decimal places from right to left, and we keep moving it till we hit the last integer, and we stop in front of the last integer. The format is you're always going to have an integer. You may have a decimal point followed by more numbers or zeros, but there's always going to be an integer up front by itself, at least, okay? So by doing that, we count the number of decimal places we got. 1, 2, 3, 4, 5, 6, and 7. 7 puts us right in front of 9, which is the last integer. We don't forget we got the 9.3, so we can type in 9.3 times 10 to the 7th power, okay? 7th power, that's how many decimal places we brought over the decimal place on the right. This is nothing more than saying 9 times 3 times 10 times 10 times 10 times 10. We got 1, 2, 3, 4, etc. 7 times 10, 7 times. Doing that, you get that number. Okay. So putting those exponents together, you end up with 10 to the 7th power. Notice the exponent is a positive number. But that means that this number here is a number greater than 1. Obviously, 93 million is a number greater than 1. Okay. All right, that's for very large numbers. We'll be using a number down the road, 6.02 times 10 to the 23rd. Imagine this. Take that decimal point, move it to the right 23 times. That give you an idea how big that number is. Okay, very, very large number. Trying to put that in your calculator would be very difficult. You just added zeros. In fact, your calculator, if you did that, it won't take it, but it will take it in scientific notation. I'm gonna go through some examples of how to do that in a calculator. So there's basically at this point like 3 different types of calculators out there. And hopefully you got 1 of the 3. All right, for very small numbers, that's numbers less than 1, the first thing to notice is that I'm going to have an exponent that is going to be a negative number. Okay, so what we do, like we did earlier, find where the decimal point is. In this case, it's over here to the far left. We count the number of decimal places until we hit stop right after the first integer we find. In this case, is a 1, and we stop immediately behind it. So it is 1.7, okay, times 10 to the negative 10. It's negative 10 because this number is less than 1. Okay, so I'm going to have a negative exponent. Okay. Now, the nice thing about scientific notation, that if you ever have a problem as far as putting a number into the correct scientific notation, into the correct number of sig figs, let me restate that if you get a number that's ambiguous, you could always convert it to scientific notation, and there's no question about it. When you're in scientific notation, you have the correct number of sig figs. Okay, so when you are converting these numbers into scientific notation, the first note to do is to see that I have 2 sig figs in that number, which means my final answer should contain 2 sig figs. Okay, don't lose anything. So it's a negative exponent, which you can tell it's a number much, much less than 1. Okay, now let's convert the following to scientific notation. Take the first one. First step number 1 is determine how many sig figs you have. For number 1, how many sig figs do we have?
6.
We got 6 sig figs. So that means that when we convert this number to scientific notation, we have to maintain the 6 sig figs. Okay, good. So now we find the decimal point, which is right here. We're going to go to the left until we stop right in front of the last integer. So we go 1 and 2. Okay, so our exponent is times 10 to the 2nd power. So we got 5.48005 times 10 to the 2nd power. Okay. All right. The next one here, we have 3 sig figs. These zeros don't count. Refresh your memory on those, right? They don't count. So we start from where the decimal point is, go from right to left. Our exponent is going to be a positive. So we go 6, we got 3 here, 6 and 7. So we got 6.81 times 10 to the 7th power meter inches. Okay. Number 3, we're going from left to right. So we're going to have a negative exponent. Okay. And this is a pint. So starting where the decimal point is, we go 1, 2, 3, and 4. So we got 3 sig figs there. So we got 4.00 times 10 to the negative 4 pints. And then this one here, we're going to move it over to scientific notation. There's only one sig fig, so we go 1, 2, and 3. So we go 2 times 10 to the 3 to the third power. Okay, so that is written with 1 sig figs. But for example, what if, for example, you got an answer of 2,000 in your mathematics, but you are given the sig figs you started off with, you're governed to present your number with 2 sig figs. But it's difficult to do that with the number 2,000. Okay, I can't make 2,000, or I can't write it with to give you 2 sig figs unless I convert it to scientific notation like so. And then all I do is 2.0 times 10 to the third. Okay. And so in this scenario, by converting it to scientific notation, I can now convert that number 2,000 to show you 2 sig figs. If I needed 3 sig figs, 2.00 times 10 to the third, etc. 4 sig figs, just keep adding another 0. Because in scientific notation, you're always in the correct number of sig figs that you need. Those are your answers right there. All right. Now, how do we do that on your calculator? Well, there are 3 types of buttons that so far I'm aware of. Okay. If I got 3 pictures here. If you look at, let me see if I get a closer look. Okay, this is a better picture here. On the far left, most of the newer calculators have a button, and I've highlighted it down there with a circle where it says times 10 to the x. Okay, times 10 to the x. Not to be confused with the button that has just 10 to the x. That is not the correct button. It has times 10 to the x. Okay. Now, other calculators have a button that have the double E letters. These are a little bit older calculators. Okay. But they have the EE button. And then if you look at Windows, there's some calculators, and even some calculators, they just Windows have a button called EXP. Okay. Those are the 3 different types of buttons in your calculator that allow you to get into the scientific notation mode. You may want to check your manual and look it up and look up scientific notation in your manual so you can show you how to input a number. Now, another button that you should be aware of in your calculator is it's a toggle button that goes from positive to negative. For example, this one here is this button right there. So if I type in a number, which is positive, and for whatever reason I want to make it negative, I hit that toggle button, and it converts it to negative, which you may need, especially if you got a negative exponent, okay? On the Windows calculator, it's this button right here. And on this calculator, it's this button right here, okay? Now, in both scenarios, all 3 scenarios I've been working with here, the buttons are the primary buttons, so they're up front. Your calculator occasionally puts scientific notation as a secondary function. So be aware of that. Maybe it's a secondary function. So if you look at the calculators on the left, the middle and the left, you have in yellow an alternative function, and the only way to access those, you gotta hit the second button, okay, to access the secondary function. So again, check your calculator and see how it works. And if you have a challenge with it, bring it to the lab and we can look at it and make sure you're familiar on how to input scientific notation on it, okay? Because we'll be using it to do calculations. All right, so all right, so let's say we're gonna input the number 2.39 times 10 to the 9th power. So in your calculator, you would type in 2.39. In fact, let me share. I'm going to share my Windows calculator with you, okay? And we were looking at inputting 2.39 times 10 to the 9th power. All right, so in this Windows calculator, you have the EXP button. So I would type in 2.39, okay? Then hit the EXP button. That puts us in scientific notation format. And so now it says E, and then this represents times 10 to whatever power. And the question was 9. So if I type in 9, this is the Windows calculator that represents 2.39 times 10 to the 9th power. Now, which is a different, notice something is 2.39 times 10 to the 9th power. This is the correct format for scientific notation. This is the format for the calculator for it to understand scientific notation. When you have an answer like this, you need to convert that E to times 10 to whatever power it is, okay? So that's the value on the right is not the correct scientific notation format. Now here's that toggle button. By hitting it back and forth, notice the number becomes negative. Positive, negative, because I could have a number that's 2.39 times 10 to the negative 9, right? So I need that toggle button to get me into the negative format. Now, once you input that number, you just do the mathematics like you normally would. Nothing special, divide it, multiply, what have you, okay? And then you got your answer. So let's take that number as positive, divided by 5.36 to the 10th power, and you end up with this number right here. Let me clear this up. I did some mathematics. I don't remember now what I'd multiplied or divided, but I ended up with this number right here. Well, I got this number here, big number, and it would be incorrect to, I'll present all this number, obviously. So this is where I would go and find whatever sig fig I was at. I think I was at 3 sig figs. So at that 5 position, starting from far left, this is where that 5 remains 5 or kicks up. And in this case, it would kick up. So my answer would be 0.0446. Okay? But never ever present or give this as an answer, this big, humongous number here. Okay, because that would be totally inaccurate. Okay. All right, let me go back. All right, so do a practice problem. You might try this at home. 2.84 times 10 to the 23rd divided by 7.24 times 10 to the 12th. Okay. And I'm gonna go ahead and clear this. Okay, hopefully write that down. I'm gonna go ahead and type it in into the calculator. Okay, so I got 2.84 exponent 23 divided. That's that number 2.84 times 10 to the 23rd divided by 7.24 exponent 12 gives me this number here. Notice this big humongous number we got. Another button in your calculator may be like FE. If I click that FE, it converts it back to scientific notation for the calculator. So 3.92 times 10 to the second power. So let me do this. Yeah, go ahead if you need graphing calculator, but you know, as long as you only need something that can do scientific notation. Graphing calculators, you know, we're not going to use that function anyway. All right, so here we have it right here. Give me a second. And that was the answer that the calculator gave me. Oh, times to the 10th power. Okay. Now, two things in looking at this is obviously that answer would not be acceptable to present on many fronts. One, the answer that the calculator gave me is not in correct scientific notation. That's point number one, because you got that E plus 10 that needs to be changed to times 10 to the 10th power. Second of all, the mathematics govern how many sig figs our answer should have. Okay, so how many sig figs should our answer have? (2.84 times 10 to the 23rd divided by 7.24 times 10 to the 12th. Okay. How many sig figs should our answer have?
2.
Double check.
3.
Yeah, okay. 2.84 has how many? 3 sig figs, right?
3.
Yeah, and 7.24 has 3 sig figs. Well, so both the numerator and the denominator have 3 sig figs. Therefore, our answer should only have 3 sig figs.
I thought
Okay.
you meant after the decimal.
Oh, okay. No, including those three, 2.84 is 3 sig figs, 7.24 is 3 sig figs. So our answer should have 3 sig figs. So we're going to truncate at the 3.92, okay, times 10. I don't have superscript, but that symbol, the caret, represents superscript. Okay, so that is the number that you will present, 3.92 times 10 to the second power. We remove the E plus because that is the format of your calculator, okay? And then convert it to scientific notation with the correct number of sig figs. Okay, let's see. Oh, 3.92 times 10. All right. So that is our practice problem. All right, so the point, sometimes it depends on the calculator. Like if you look at this answer, that you do the mathematics and your calculator outputs this answer like that on your little LED readout. Okay, well, that is not the correct scientific notation format. You would take that number and 1.2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 8th power. You need to convert that to the correct format. Okay, assuming that's the correct number of sig figs, you need to truncate. Okay, so the other thing too to remember, depends on your calculator. It could be a secondary function with respect to scientific notation. My suggestion is look at your manual, and if you don't have a manual, you can check the internet. 9 times out of 10, you can find one there. And if that all fails, bring it in and into the lab, and we'll go through it. We'll figure it out. Okay. All right. Any questions about that? We're almost done with this chapter here. We're buzzing along, aren't we? The last aspect about this particular chapter deals with percent. And I think you're more familiar with this already. You have a test. You got a 100-point question, right? You get, 80 points out of 100. What's your percentage? Your 100 questions, you got 80 right. What's your percentage? Exactly, 80. So the percentage here is just no different. You're going to have a part divided by a whole times 100. Okay, be it gold, like we're going to do that example, or be it grades. Okay, be it grades. So, for example, in this case here, you have a gold ring, has a total mass of 239.45 grams. It underwent analysis and determined that there's 198.38 grams of pure gold in that big chunk of a big ring. Okay, so the percentage of gold for this ring is as follows: 198.38 divided by 239.5 times 100 gives you this big old number, which of course is incorrect to present because you're governed by the number of sig figs in your mathematics. So 198.38 contains 5 sig figs. 239.45 contains 5 sig figs. So the numerator and denominator both have 5 sig figs. Your answer should have no more than 5 sig figs. Okay. And so the final answer is 82.848 because you need to truncate it or cut it off. Truncate, cut it off at the 5 sig fig position. 1, 2, 3, 4, right here. Okay, so we got 5 sig figs in both cases. Okay, remember when you multiply and divide, the number with the least number of sig figs will govern how many sig figs your answer has. If they both had the same number of sig figs, then so be it. Your answer had the same number of sig figs. Okay. All right. And congratulations. We are done with chapter. We're running right through here. Done with chapter 5. Let us take a little break. Chapter 5. 2. And then okay. Let me share. Now, this particular chapter, chapter 3, deals with metric units and conversions. And this aspect is that we are converting from either within the metric units, or we're going from either English units to metric units. But the main point of this exercise here is to be able to get from one set of units to the other, because we're going to use the same technique when it comes to chemical reactions. And you might be wondering, what exactly are you talking about here, Dr. Fred? So let me do this. Let's say we have a hypothetical reaction of A plus maybe 2 B's react to give me 3 C's plus maybe 1 D, okay? So what we're gonna do is say, for example, if I start off with 10 grams of A, how many grams of D would I create in this particular reaction, okay? And, or it could be if I start off with 5 grams of B, well, how many grams of A do I need for this reaction to proceed? Okay. And we're going to use the technique that we're going to do in this particular chapter of, first of all, writing down what we're given, look at the units with respect to what we're looking for, and then putting in conversion factors in between to cancel the units of what we're given to eventually get to the units that we're looking for. So basically you can solve the problem by just keeping track of your units. Okay. Well, before we get into the chapter, let me talk a little bit about the metric units, because that seems to be a challenge also with respect to students. It's the irony of this whole metric system is that the US has been trying to convert to metric units since I was a kid. That's 100 years ago. And it still hasn't happened. But yet we go through life, here that we can go get 2-liter bottle of soda pop, but then, turn around and get a gallon of water or a gallon of milk. So it's like the units, where we get a mixture of units. Well, anyway, let me talk about that. Now, this particular file is on chapter 3, in chapter 3 module. So you have a copy, okay? And what I've done here is I've taken mass, volume, and length. All right, so the most common unit that we utilize with respect to mass, where'd it go, is G for grams, okay? The most common lowercase g, the most common unit for volume is capital L for liters. Okay. And then for length, we're looking at meters. Okay, so we got G for grams, L for liters, and M for length. Now, 1 kilogram is equal to 1,000 grams. Also, 1 kiloliter is equal to 1,000 liters, and 1 kilometer is equal to 1,000 meters, okay? Now, we have prefixes of D, C, M, and U. Now, C stands for deci. Does anybody know how many years in a decade? One decade has how many years?
10.
Exactly. And so check this out. 10 decigrams in 1 gram. 10 decigrams in 1 gram. How many years in a century?
50.
Oh, no, not quite. 1 century.
100.
100, exactly. So now check this out. In 1 centigram, there's 100 centigrams in 1 gram. And how many years in the millennium? Anybody know? Take a wild guess. The answer is right there.
1,000?
Exactly. In one, yeah, there's 1,000 milligrams in 1 gram. Okay, as there is 1,000 years in the millennium. And so using the prefixes, you can see where the number that you need is right there. 10 decigrams is 1 gram. 100 centigrams is 1 gram in 1 gram. 100 milligrams in 1 gram. The one you may not know or not heard of is micro. It looks like a letter U, but it's got a little tip in the front of it. So there are 1 million micrograms in 1 gram. Okay. Now, if you take those prefixes and just move them over to the center in volume, same thing. 10 deciliters in 1 liter, 100 centiliters in a liter, 1,000 milliliters in a liter, and 1 million microliters in 1 liter. And take those prefixes again and pass them over, move them over to length. So we have 10 decimeters in 1 meter, 100 centimeters in a meter, 1,000 millimeters in 1 meter, and 1 million micrometers in 1 liter. Okay, so all the prefixes, the nice thing about the metric system, I can go from one set of units to the other without too much of a problem. Now, the point of all this is that every one of those conversion factors, every one of them is a conversion factor. Okay, for example, the very first one, 1 gram in 1,000 grams. I can write that in 1 or 2 ways. I can write it with kilograms in the numerator, or I can write it with kilograms in the denominator. Okay? And this is true for every one of these conversion factors that we got here. It's another ratio. Back to the ratios. Any ratio I can write. Now, you might be tempted to invert that 1,000 and don't do that. Just whatever integer that number that is, just keep it, whether you put in the numerator, whether you put in the denominator, okay? Don't try to invert it, just keep it at that. Now, there are some of you that are gonna try this A plus B equals C over D, which is okay, there's nothing problem with that. However, that is good for the first conversion. And what can happen if you continue for the second conversion, things can get turned around. So I don't recommend this system to solve your problems. What I do recommend is taking the conversion factors that you have and set them up in parentheses like I've got them set here, and then follow your units. Okay. Follow your units. So you start off with the X number of units you're given, and you're trying to find an X number of units, what you're looking for. And by putting conversion factors in between, you're able to cancel things out and get to the units that you're looking for. For example, let's do a quick example here. The question is, how many micrograms are in 0.125 kilograms? Okay. Well, I set my problem up as follows. Okay. I write down what I'm given, 0.125 kilograms. I look for a conversion factor that gets me out of kilograms into another unit. Well, I got a conversion factor that there are 1,000 grams in 1 kilogram. So in doing that, my kilograms cancel, leaving me with grams. Then I know from the conversion factors up top that there are 1 million micrograms in the gram. So I set that final conversion factor such that my grams cancel, okay? Leaving me unit-wise of micrograms, which is what the problem asked for. See, I started off with what I'm given right here, and I end up with the units that I'm looking for, okay? Now, all of these conversion factors are exact numbers and therefore will not play a role in sig figs. So we have 0.125 kilograms, which is 3 sig figs, so our answer should have 3 sig figs, okay? All right, So notice how you can convert anything, apples to oranges, as long as you have conversion factors. And I have an extreme example to utilize for you. All right, so here are our units that now we give you conversion factors in the shapes table. You'll find conversion factors of 1 inch is equal to 2.5 centimeters. That's going from English to metric. 1 pound is equal to 454 grams, and 1 quart is equal to 946 milliliters. Those are the conversion factors that go from English to units. We give this, those are given to you, but within the units, within the English units, within the metric units, that's on you. Okay, so like that table I just gave you up on first page, be familiar with that in case you need it. For every one of these conversion factors, notice it's a ratio, okay? And I can write it in any manner that I need, depending on the question asked and what units I'm looking for. These are ratios that are what we talked about, if it's salary, I'm getting, you're working $50 an hour. I can write it $50 per hour or dollar per hour or hour per dollar, inverted, okay? And by keeping track of my units, I'm able to figure out what I need to do. This was a quick algebra review. I think I went through that earlier. So that's just to make sure that you are familiar with your units cancel properly. All right, so what I'm going to do next is the following. I'm going to give you an extreme example of going from one set of units to the other, okay? And the point of this exercise is to demonstrate to you that as long as I have conversion factors, ratios, to go from one to the other, I can convert units. For example, I think I mentioned this earlier. I said I used this as an example when I was working, teaching chemistry to dental hygiene students at Carrington College. Said, okay, given the following conversion factor, and I kept it because it really shows how extreme this conversion factor is. Given the following conversion factors, how many DH students equal 4.5 bananas? Okay, pretty crazy, huh? Well, not so crazy because I got conversion factors. I have a conversion factor that says that 1 DH student is equal to 6 grapes. Okay. I also have a factor that says 3.5 grapes is equal to 1 orange. Excuse my English improper use, 1 orange. And that 1 orange is equal to 6 toothbrushes. And the 3 toothbrushes is equal to 1 banana. Okay, so there's my conversion factors. So what do? I can set, here's my conversion factors. Let's set up the problem. Okay, first thing is I'm given 4.5 bananas. That's in the problem, 4.5 bananas. All right, so based on my conversion factors, I look for something, a conversion factor that get rid of bananas and give me some other units. Well, I have one. I have one that 3 toothbrushes is equal to 1 banana. Okay, wild, right? But check this out. Bananas cancel when they do the mathematics. And if I were to stop the mathematics at this point, the units I've converted to has been to toothbrushes. But that's not where I need to go because eventually I need to go way over here to DH students. Okay, so I got to add another factor in here to get rid of toothbrush and put me into another unit. And I have one that says that there are 6 toothbrushes per 1 orange. Notice how I set that up. I set that up that the next factor has to have the units I need to cancel in the denominator. Okay, pretty straightforward like that. My bananas cancel, toothbrushes cancel, unit-wise, I'm in oranges. So, but I'm not at where I need to be. The DH students, I'm in orange, so I need another factor to get rid of orange. So whatever factor I picked, I gotta make sure it's oranges in the denominator, okay? Because I want those to cancel out when I multiply by the next factor. And sure enough, there's the other factor. where oranges cancel, leaving me with units of grapes. All the other units cancel. I'm not even done the math yet. All I'm doing right now is setting up the problem with my units properly set up and making sure that units are canceling out. This is the typical type of problem set up when we're dealing with chemical calculations, like I explained earlier, on how we're going from reactant to product and so forth, okay? All right. So then the next thing is, at this point, I am in units of grapes, which obviously I'm not in the final units that I need to be at. And so I have one final factor where 1 DH student is equal to 6 grapes. I go back and I double check, make sure my units cancel out. Okay. Notice I did not convert these numbers like the 6 and the 3 or the 6 to another number. I'm going to take the inverse of that. No, just stick them in either numerator and denominator, wherever they need to be. Okay. I double check my units. My units all cancel out properly. And guess what? At the end, when the math's all done, I'm at the units that I need, which is DH students. So now I can do the math. Okay. And that gets me to 3.3 DH students. And so 4.5 bananas is equivalent to the 1.3 DH students. Okay. The first totally unrelated to each other, the bananas versus human beings, but I have conversion factors, okay? And the extreme aspect of this is to demonstrate to you when we get to chemical reactions that it's going to look just as bad, like I can't get from point A to point B. Well, yes, you can, by keeping track of the units, okay? So this is, like I stated, a very extreme example of conversion factors. All right, so this is also in the module, okay? So you can go through it and help you out. So chapter 3, conversion, metric units and conversion. You know what? I just realized the time, it's 4:15. Why don't we just stop it here? And I'll load up chapter 2, which is changed, and we'll start chapter 3 come Tuesday, okay? I may touch upon some of this information during the lab, because there's some information you may need concerning sig figs and so forth in the lab. And that's what the next lab is all about accuracy and how which measurement is a lot more accurate than the other. Okay, so let us just stop it here because I got 5 minutes and we'll leave it at that. Any questions?